In this problem, we are asked to find the adiabatic equilibrium temperature and the corresponding equilibrium conversion. Let us read the problem. A liquid phase exothermic reversible reaction R giving rise to S and S giving rise to R is to be carried out at adiabatic conditions. Heat evolution during the reaction is minus 98 kJ per mole. Specific heat of the reactants and products are the same and they can be considered to be constant at 215 joule per mole Kelvin. Value of equilibrium constant at 25 degrees Celsius is 95. That is K is 95 at 25 degrees Celsius. The feed to the reactor is pure reactant A, of course A is missing, at 30 degrees Celsius. Pure reactant, of course, what is it? Reactant is R. Feed is at 30 degrees Celsius. We are asked to find the adiabatic equilibrium temperature, adiabatic equilibrium temperature and the corresponding conversion. R is given as 8.314 joule per mole Kelvin. Okay, so what is expected is we need to find the adiabatic equilibrium temperature. What is the meaning of that? Let's quickly go to the end result and see. Say adiabatic equilibrium temperature, the feed is entering at 30 degrees Celsius. We need to find the exit temperature such that this exit is leaving at equilibrium. This is a equilibrium curve, or is it equilibrium conversion versus temperature plot. In the plot, this adiabatic operating line is going to just meet this meeting point. Or we are going to find this temperature and the corresponding conversion. So what are all needed? We need to get the equation for the line as well as the plot of XAE versus temperature. So that is two tasks. First, let us get the equation for the operating line. So for that, we need to know the heat of reaction at the reaction temperature. So the relation for heat of reaction at any temperature is heat of reaction at 298 Kelvin plus specific heat of products minus reactants into delta T. So CP of the both the components are the same, which leads to this term going to 0. So we have delta HR at any temperature is delta HR at 298 Kelvin. So this is available. So what is the heat balance equation? Simply heat of reaction at the exit temperature, there is exit temperature, multiply by conversion of A, the key component, that is equal to Cp of the feed multiplied by delta T. So this is heat of reaction, heat generated per mole of A getting converted, that is equal to the heat needed to rise the feed from its initial temperature to the exit temperature. So the Cp of feed is given as 215 joule per mole Kelvin and delta HR is given as minus 98 kilojoule per mole. Better to convert them to the same units. So multiply this minus 98 with 1000. So we have this 98,000. So this is minus delta HR. So already delta HR is having negative and we have totally positive now. Okay. So otherwise this is the equation of the operating line. So otherwise we have the plot of XAE or sorry what is it XA versus temperature and we want to get that we want to get the equilibrium, we want to get this point as well as this point. So there are two unknowns here. No? So how to find that? Of course, we can draw a line starting from a temperature of 30 degrees Celsius and to which temperature and to which XA. So otherwise since otherwise we cannot solve this equation without additional equation. That additional equation is nothing but this curve we can obtain what is called the equilibrium curve from the data of, okay, we'll come to this point, we will come to this. Before that, let us get the equilibrium curve generate, what is the equilibrium curve conversion versus T generated, with XAE versus T to be generated. For that we are writing the equation again from, and we know this capital K is related with equilibrium conversion by this way, and capital K as a function of temperature can be obtained from this want-off equation. Of course, here delta HR is remaining constant. So that's why this equation is very simple. So we know this 298 Kelvin. We have this K is at 298, K is 95, and substituting that we have K as a function of temperature. So otherwise we can make a table of starting from a temperature of 10 degrees Celsius to the whatever the temperature. Okay, you can take a range of temperature. Of course, temperature has to be again converted into Kelvin to get the values of K. This is T in Kelvin. Okay. So here T is given in Celsius and T in Kelvin you take and get the values of K, and the corresponding XAE, that is at any temperature get the equilibrium conversion from this formula. Of course, this formula you can derive. Okay, the derivation of this is given in another workout that you can refer. So now we have the expression for K as a function of temperature. Using that we have K as a function of temperature is the calculated, and the corresponding equilibrium conversion is also calculated. So otherwise we have what we have, this curve generated. Now already we have this equation of the line. So the starting point is given as 30 degrees Celsius. We want to draw a line with a slope of delta HR by, what is it, the slope? Delta H, the slope of this line is, this is y, like y equal to mx plus c, or the xa is equal to this m into, what is it? Otherwise, say we need to draw this line. So for that, what we can do, rearrange to the form. Initial at a temperature of 30 degrees Celsius, conversion is simply 0, and at a temperature of T2, conversion is XAE. So we are going to find this XAE and the corresponding temperature. That's a target. So the slope is known. So we need to, starting from the point of 30 degrees Celsius, draw a line with a slope of this 215 by 98,000. So how to draw that? That is a tricky thing. Not so tricky, but say we can easily do that. Say this XAE by 2, or this is equation. This you can take it as delta y by delta x. Now this is delta y by delta x equal to this value. And we can assume some value of temperature difference. Say for a temperature difference of 60 degrees Celsius, what is a y coming? So we can, now we have two temperature values and two XA values. So at a temperature of 0, of course this is XA, and here also the XA. Okay. So at temperature of 30 degrees Celsius, XA is 0, and at a temperature of 90 degrees Celsius, XA is 0.1316. Otherwise, this point and this point are marked in the plot. Simply draw a line passing through these 2 points, and that is cutting this equilibrium curve. This intersection point is the final result. So this intersection point is noted from this graph. So what is the value? The exit temperature is coming as 84 degrees Celsius, and the corresponding conversion is noted from the plot. So this straight line. Okay, so that is coming to 0.12, which is 12%. So what is again quickly go through. So this is a reversible exothermic reaction. We are asked to find the adiabatic equilibrium temperature. We are given with the inlet temperature of the feed. We are also given with heat of reaction and specific heat, and K at one temperature is known. We can generate K values at any other temperature using the values of delta H using want-off equation. So we have K as a function of temperature available. So once K as a function of temperature is available, XA as a function of temperature is obtained. So we have this equilibrium curve generated. XAE versus T generated. We also have this equation of adiabatic operation line. What is it? Adiabatic the reaction is going to happen in a adiabatic reactor. So adiabatic operating line is obtained from the heat balance, so which is what is it, heat evolution per mole of A converted, that is equal to Cp of feed into delta T. So this equation is plotted. So that is simply a straight line, and this curve, the intersection point is read from the graph. Okay, good. Thank you.